Good day to everyone. Today we are going to discuss part 2 of Module 1, Unit 2 of the subject CE 4111. So in this module, we'll be discussing the design requirements of a highway pertaining to minimum radius of curvature. The third element that we consider in the design of highways is the minimum radius of curvature. So in designing highways, we do not only design straight highways, but basically this will be a combination of different curves and straight lines. So in the design of highways, smooth flowing curves would often be desired since this would give an easier maneuver to drivers or road users. Though the cost of smooth flowing curves will be too prohibitive as this is very expensive. Existing structures or terrain will now prevent the design of gentle curves in our highway sections. Thus, it is necessary for us to determine the minimum radius of curvature that would give us ample time to react on obstructions, different types of vehicles that would be on the same road, and likewise, the minimum radius of curvature will help us to arrive at our desired speed. In minimum radius of curvature, we follow the mass point formula, which is the relationship between the design speed and the curvature and the joint relation of the superelevation and the side friction. So the derivation for the equation we use in determining the minimum radius of curvature can be taken from the horizontal curves that we have learned in engineering surveys. So from engineering surveys, we have your radius, and from here and your internal angles, we can now identify your point of curve and your point of tangencies. So applying this curve in highway engineering, will now have your highway design. So basically, the radius is measured from the center of the curve towards the center line of the highway. And from there, we'll now have your length of curve. So applying now, when vehicles move along this inner lane of the highway, it will now experience a obstruction or site obstruction at this area. So your SSD now, this SSD will lie along the center line of the inner lane, which is what we call your critical inside lane. Critical since the vehicles passing through this inside lane will be more vulnerable to the obstruction which is inside the radius or inside the curve. So looking now at this diagram, our minimum radius of curvature to consider will be RV, and from the diagram, RV can be computed simply as the radius, which is measured from the center to the center line of the roadway, minus 1/2 of your lane width. So another way to determine the minimum radius of curvature is by considering all forces acting on a vehicle when passing a horizontal curve. So, when a vehicle would pass through the curved section of the roadway, usually this will be happening on an incline. So from this figure, we'll have now the following forces. The first one is the weight of the vehicle. Next, we have your centrifugal force, or CF, which is simply the force that would pull away the vehicle from the center of the road. Without the centrifugal force, the vehicle would tend to overturn on the road section while maneuvering. So the centrifugal force will simply be equivalent to the weight of the vehicle times its speed squared divided by GR. So other forces that would act on the vehicle while maneuvering your horizontal curve is your friction, or in this manner, we have your side friction, which will act on between the surface of the road and your tires. The side friction is sometimes called your skid resistance. And the last force that we will consider in this diagram will be your normal force. So considering the forces acting on the vehicle at its center of gravity, so we'll have now our centrifugal force and the weight. So from here, we'll now be able to identify the centrifugal ratio, which is simply the ratio between the centrifugal force and the weight. So aside from this equation, which is WB squared over GR all over W, we can also take the centrifugal ratio in terms of as a ratio or as a resultant of the forces CF and W. So in these regards, we'll be able to relate now our centrifugal ratio in terms of the angle of friction and your angle of inclination. So if we are moving now the centrifugal force on this side in order to create a force triangle, we can see that CF divided by W is given as the tangent of alpha plus theta. So with that, the centrifugal ratio and the resultant is now equal to the tangent of alpha plus theta equal to v squared all over GR. So next, taking into consideration the forces acting on the vehicle at the surface, we have now our skid resistance or the friction divided by your normal force from your physics. So as the vehicle moves along your horizontal curve, the normal force now will be considered as negligible. Thus, tangent of alpha now is taken as an equivalent of the skid resistance Fs. So from the figure, we can now take that the tangent of theta is equal to E divided by unit 1. So considering now the equation from centrifugal ratio, tangent alpha plus theta, so from trigonometric identities, the sum of the tangent of the sum of two angles is taken as tangent alpha plus tangent theta all over 1 minus tangent alpha tangent theta. So from this side of our derivation, we can see that tangent alpha is equal to Fs, tangent theta is also equal to E. So substituting our values, we now have Fs plus E divided by 1 minus E times Fs. So from here, tangent alpha plus theta is also equal to v squared over GR. So equating now this one, so we arrive at this equation. So take note for E times Fs, since they are tangent values, so they will become very small, multiply to each other, they will now be approximately equal to 0. So with that, If EFS is equal to 0, so 1 minus 0, then we can now derive V squared divided by GR is equal to Fs plus E. So given now our derived equation, the ideal angle of embankment for any horizontal curve means we have an alpha or angle of friction equal to 0. So therefore, we'll now have the ideal embankment is equal to the tangent of theta, where inclination is equal to V squared all over GR. And likewise, the maximum speed of a vehicle which can maneuver without skidding or without overturning will simply be equal to tangent of alpha plus theta is equal to V squared all over GR. And for your minimum radius of curvature, that will now be equal to V squared over G times E plus Fs. If we have mixed units in our equation, meaning the speed is given in kilometers per hour and the radius will now be in meters, then our equation for the minimum radius of curvature will now be equivalent to V squared all over 127 times E plus Fs. So in table 6.4, we are given the different values of the side friction for different design speed. So in your modules, we also have table 6.4, but it will have different values as those values are from the 1984 version or edition of the AASHTO guidelines for geometric design of highways. So this one is the more updated one, as this is from the 1994 edition. Next, we have table 6.5, which is the recommended minimum radius of curvature for different design speed. As well, same as well, this is taken from the 1994 edition of the AASHTO guideline for geometric design of highways. So in computing now for your minimum radius of curvature per design speed, you can now check if your computed minimum radius is within the given recommended values. So to understand the minimum radius of curvature further, let us solve some examples. The rated speed of a highway curve 100 meters in radius is 65 kilometers per hour. If the coefficient of friction between the tires and the road is 0.6, what is the maximum speed at which a car can maneuver the curve without skidding? So from the problem, we are given the radius, which is 100 meters, the design speed at 65 kph. We're also given the coefficient of friction, 0.6. So from here, we can now get our angle of friction from tangent of alpha. So the alpha now is equal to 31 degrees. So for the maximum speed without skidding, that is now equal to the tangent of theta plus alpha is equal to V squared divided by GR. So we know already the alpha, but we do not know your theta. So theta now will be taken from the ideal angle of embankment. So when alpha is equal to 0, then tangent theta is equal to 65 divided by 3.6 squared divided by 9.81 divided by 100, giving us a value of theta equal to 18.4 degrees. So substituting now alpha and theta in the equation, we now have tangent 18.4 plus 31 is equal to the design speed or the maximum speed V squared divided by GR. So V now is equal to 33.82 meters per second. Or converting this, we now have V maximum is equal to 121.75 kilometers per hour. We have example number 2. Determine the radius of a horizontal curve for a design speed of 50 kph as specified by the specifications in lateral friction and superelevation. So in this problem, we are given the design speed equal to 50 kph. So for our lateral friction or side friction, this will be taken from table 6.4. So for our solution, we know that the equation for your minimum radius is equal to v squared all over 127 plus fs. So for fs, we can get it from the table 6.4, while for the value of e, this will be taken from AASHTO recommendations, which gives us that the maximum e is ranging from 6% to 12%. So in this manner, we'll now be using for our frictional force that will be equivalent to 0.16, taking from 6.4. So for A, design speed of 50, equivalent frictional force is 0.16, and for our super elevation E, we'll now be using the lower limit of your Emax, which is 6%. So substituting now 0.16 and 0.06 in the equation of our mean, we'll now have 50 squared all over 127 times 0.06 plus 0.16, and now arrive at a minimum radius of 89.48. So next, example number 3. What is the minimum radius of a curve which has a design speed of 110 kph and super elevation of 6%? So we are given design speed 120 kph and super elevation 6%. So for our side friction, we're going to use again table 6.4. So for our solution, for the required radius of curvature minimum, we simply apply again the equation of v squared over 127 plus e times e plus fs. So we are given v, we are given e, so the only value we need to look for is the side friction. So our design speed is at 120, so the side friction now is equal to 0.09. So substituting our value, we now have our mean is equal to 120 squared divided by 127 plus 0.6 plus 0.9. So giving us a value of 755.906 meters. So take note that the module is using AASHTO 1984, so the answer will vary. The answer in your module will vary with the answer that we have computed in this lecture. So next, we have a curve is to be designed to have a design speed of 100 kph. If there is no super elevation, what would be a safe radius for curvature? If the curve is designed with super elevation 3%, what would be the minimum radius of curvature? So for given, we have 100 kph design speed. For our required, we want to solve for the minimum radius is if E is 0 and if E is 3%. So for your side friction, we are going to use again 6.4 given 100 kph, so we'll be using 0.12 as the fs. So for our solution, we'll be using general equation for our mean v squared over 127e plus fs. So ang magbabago lang is the value of e. So if we have e equal to 0%, then that will simply be 100 squared divided by 127 times 0.12, giving us a value of 656.168. So if we have E is equal to 3%, Then our mean now is equal to 100 squared divided by 127 plus times 0.03 plus 0.12, which will give us an answer of 524.93. So again, this answer will be different in the module, as for the module it is using AASHTO 1984. So last example for minimum radius of curvature. What is the minimum radius of curvature allowable for a roadway with 100 kph design speed, assuming that the maximum allowable super elevation rate is 0.12. So compare this with the minimum curve radius as recommended by AASHTO. So for our given, we have the design speed at 100 kph. We have your super elevation at 0.12. So from table 6.4, the frictional force for a design speed of 100 is 0.12. So for our solution, we have R mean is equal to V squared divided by 127 times E plus Fs. So with that, now substitute the values of V, E, and Fs. So we'll arrive at R mean equal to 328.084 meters. So from table 6.5, the minimum radius for a design speed of 100 kph is 490 meters, which is greater than our computed value. So what does it mean? Yung computed natin is mas maliit compared dun sa recommended ng AASHTO for 100 kph. Therefore, we have to recompute for the actual super elevation that we have to use in our design. So for your reference, you can check on the book of Sigwa or this site for geometric design. And then for our evaluate, please answer the evaluate problem of radius of curvature. And for your additional problem, we have problem 1 and problem 2.